Hello, how are we doing? And in in this video, I really want to take a couple minutes out and point out a singular point. And a singular point is a special point we defined earlier in terms of a parametric curve, such that the derivative dx dt over dy dt is equal to 0 over 0. And we said that there is nothing here that can really help us identify when this occurs graphically. They tend to be weird situations. You have no change in x, you have no change in y. This is a singular point. So in this curve here, as we're going to look at an example, is one of my favorite curves. I love semi-cubical parabolas. They're one of my favorites. I know it's weird to have a favorite. Maybe I just like it so much because it's fun to say semi-cubical parabola. But let's go ahead and look at x equals to t squared and y equals to t cubed. And we are going to look at this from negative infinity to infinity. So as I said before, this is called semi-cubical parabola. Semi-cubical parabola, and we could actually convert this to a normal curve by cubing x and squaring y. So if we were to cube x, we would have x cubed equals t to the 6. If we were to square y, we'd have y squared equals to t to the 6. T to the 6 has to equal t to the 6, so we know this is the relationship of x cubed equals to y squared. So we could actually graph this by graphing the positive and negative of x to the 3/2 power. So when we look at this, we have x to the 3/2 power. What does this guy look like? He is a semi-cubical parabola. So a semi-cubical parabola looks something like this. So he opens up like that, and then he does the same thing going down right here. I bet we can look at this right off the bat, and we could figure out exactly where we have our point that causes some confusion. So those points are not always the easiest to identify. However, we can do them algebraically by determining where dx dt and dy dt both equal to 0. So by finding dx dt, so we're going to take the derivative of x with respect to t, and this is going to equal to 2t, and then we're going to find dy dt, and this will be 3t squared. I hope when we set these both equal to 0, we get t equals to 0 and t equals to 0. So we're going to have a singular value when t equals to 0, which is going to be right here. So it's one of those v's. It's a cusp that definitely stands out to me. So we're going to have this issue here at the origin, and that's going to be when t equals to 0. So relatively easy to figure out, nothing that's too tough for us to do. If you would have found dy dx by taking 3t squared and dividing it by 2t, you would have seen that one of the t's cancels. A t cancels. So whenever a factor cancels, that's another indicator algebraically that we're going to have another point that is singular. So when that t cancels or a factor of t cancels, you're going to have another singular point. So in the next portion of this video, I'm going to find the first derivative at a couple points. So let's say, and I'm not going to do second derivative because second derivative is a little bit tricky. So second derivative is a little bit tricky. We're only going to do first derivative of this parametric curve at a couple points. So we'll say without eliminating parameters. So without eliminating parameters, let us find dy dx at 1, 1 and 1, -1. So the second derivative is going to be slightly different than the first. So the first thing here is that I feel really comfortable figuring out dy dx, which is the derivative of y with respect to t over the derivative of x with respect to t. And we said this was equal to derivative of y, 3t squared over 2t, 3t squared all over 2t, which is equal to 3t all over 2. But notice this is a relation of the parameter t, and we have this in terms of x and y. So going back to our original relation, we have x equals to t squared and y equals to t cubed. Let us look at our first point, 1, 1. So let us look at 1, 1. So when x is 1, we know that 1 is equal to t squared. Solving for t, we know t is equal to plus or minus 1. So t squared will equal to 1 in two circumstances, when t equals to 1 and t equals negative 1. That's not so bad. Now looking at the y parameter, we know 1 equals to t cubed. However, t cubed will equal to 1 only when t equals to 1. Where do these two match? When t equals to 1. So 1, 1 corresponds to the parameter t equals to 1. So let's go ahead and look at 1, negative 1. Again, we're going to plug into, where are we? So 1 equals to t squared. This will only occur when t equals 20. Take the square root of both sides. Yeah, take the square root of both sides. And then when we look at negative 1 equals to t cubed, I think I did this right. Sorry about that. So if I solve here, if 1 equals t squared, that implies t equals to plus or minus 1. And then I forgot to add the plus or minus. I need something to look funny. But when you solve t cubed equals to negative 1, this will only exist when t equals to negative 1. When do these values occur simultaneously? Is at the point t equals to negative 1. So therefore, the point 1, negative 1 corresponds to t equaling to negative 1. T equaling to negative 1. If we want to find dy dx at 1, 1, this is the same thing as when t equals to 1. We're just going to have 3 times 1 over 2, which is 3 halves. If we want to find dy dx at the point t equals to negative 1, we're going to have 3 times negative 1 all over 2, which is negative 3 halves. So here there's a little bit more discussion when it comes to how to actually plug in, and it takes a little bit more time when we have to go from our xy point back to our t values. So we're going from our xy points back to our t values. And the nice thing about this is that we know this will only exist at one circumstance, as this definition. Get in the habit of thinking about this in both the parameters and in terms of our normal functional curves. So they will be easy for us to start thinking back and forth. So we'll be able to go back and forth pretty quickly as we start practicing. And I know very similar to some of us might see the line as y equals tx being this nice linear function, or y equals to x squared as being this parabolic function. We're going to start being able to look at some of these same similar outcomes, like when we look at x equals to cosine of t and y equals to sine of t being a circle. Unit length 1, unit of radius, the radius being equal to 1. Very similar. So some of these parametric equations can show to us very similarly as our normal curves can as well. In the next video, we're going to be able to, I want us to be able to calculate d squared y over dx squared, the second derivative. And there's a common mistake here, is that our common mistake we're actually going to avoid is that people often think that d squared y over dx squared is d squared y over dt squared divided by d squared x over dt squared, and that is not true. So definitely take a second to think about this. Maybe rewatch this video, and then in the last video of this section, we will discuss how to find the second derivative of these parametric curves.